In this part of the text, I described some results relevant to random sampling. And what I did is I randomly sampled from a population of 100,000 observations with a mean or a population mean of 7.31. And I did these random samples across several sample sizes. So the lowest sample size was a sample size of 5, and the highest sample size was a sample size of 5,000. So what I did literally is I created a data file that had 100,000 cases. So I'm not going to go all the way down, but you'll just have to trust me that there are 100,000 cases in this data file. And I randomly sampled using an algorithm within this program SPSS, a random sample of 7 observations from these 100,000 cases. So I went into data, select cases, random sample of cases, sample, and I inputted here 5 cases from the first 100,000. And I click continue, OK. And what the program does is that it uses a filter, or it creates a filter, and many of these cases are not going to be selected. In fact, only 5 of them are going to be selected. And I'll show you which 5 in this case were selected by sorting the data. I'm going to descend, and here they are. So these are the 5 cases that were randomly sampled with an algorithm within the program, and it was a case with number of hours 8, 6, 8, and 9, and 6. And I did that once and I got a mean of 6.60. Now each sample of 5 is not going to necessarily be the same mean value. In fact, they'll vary from sample to sample. But in the instance that I did it for the textbook, I got a mean of 6.6 from those 5 cases I randomly sampled from the population of 100,000 cases, which had a population mean of 7.31. So in this instance where I randomly sampled 5 cases, which won't necessarily be the same average as that observed here, so we've got 8, 6, 8. Let's just sort this out to be sure. We got 8 plus 6 plus 8, 9, and 6. We divide that by 5, we get 7.4, and that is different obviously to the sample mean that I got from the first time that I did it. And I talk about that later in the textbook about how that fluctuates. In fact, I did it for 10 different cases in a following table. In the case where I did it in the textbook, I had 6.6 as the mean, which is a deviation of negative 0.71 from the population mean. So 6.60 minus 7.31 equals negative 0.71, right? Let's just do that to make sure. 6.60 minus 7.31 equals negative 0.71. And then I did the same thing to get 10 cases. So I actually chose 10 this time, 10 cases from the first 100,000, continue, and I can sort that again, and we'll see those 10 observations. So these are 10 random cases taken from the population of 100,000. We can see the mean here was 8.30. Now the deviation happened to be when I randomly sampled that 10, which is not going to be equal to the same 10 that I got this time. The deviation was 0.99 from 7.31. So 8.30 minus 7.31 equals 0.99. And that's the deviation between the sample mean and the population mean. A sample mean is denoted with the symbol M italicized here. So these are all the sample means. And we can see that there's a trend, although it's not perfectly consistent, for the sample mean to be closer to the population mean as the sample size gets larger. So at 100, the deviation was reduced down to negative 0.13 because 7.18 was the mean I calculated from the 100 random cases I selected from the population of 100,000. And then once we get to 5,000 cases, we're getting extremely close to the population mean of 7.31. So that was the purpose of me creating this table, was to show you that you can calculate randomly sampled data from a population in a computer program. And as the sample size gets larger, there's a tendency for the deviation between the sample mean and the population mean to get smaller, 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 although it's not perfectly consistent across sample sizes.